Gopal Ram, sir?
Yes, sir.
Okay. Are you ready, sir?
Yes, sir. Ready, sir.
My voice is audible, sir?
Yes. Am I clearly audible?
Yes, sir.
Thank you, sir.
Dear participants, please mute your audio and video. Dear participants, please mute your audio and video. Dr. Kalavati, madam.
Yes, sir.
Okay, madam. Okay, madam. 3 minutes more, madam.
Yes, sir.
Sharply 5 o'clock, we have to start, ma'am.
Okay, sir.
Thank you, ma'am. Thank you. Jayalakshmi, madam.
Yes, sir.
Okay. Suryakala, madam. Dr. Suryakala, madam.
Take the sir.
Okay, ma'am. Okay, ma'am. Thank you.
Ah,
You are all ready. Okay. Thank you. Sharply 5 o'clock, we have to start, ma'am. Thank you. Dr. Gopal Ram, sir.
Yes.
Okay. Thank you, sir.
Good evening to each and every one of you for being here with us today for Faculty Development Program. Rajapalayam Rajus College, Department of Physics is much delighted to welcome our Chief Guest, Dr.S.D.Gopal Ram, all the faculty members of Physics Department and all the participants. You are welcome for this program. Let me introduce a chief guest who is with us to deliver role of nanomaterials in lighting display and communication devices. Sir has done his postdoctoral in Allahabad University, MPhil in PSG College of Arts and Science, MSc in Allahabad University, BSc in Vivekananda College. His title of PhD thesis is about investigations on growth kinetics of zinc oxide nanostructures by hydrothermal method. And his professional work experience is postdoctoral international researcher, School of Physics and Information Engineering in Fulo University, Fujian, China, from March 2016 to February 2017. He is a research professor in Quantum Semiconductor Research Center, Dongku University, Seoul, South Korea, from September 2012 to August 2015. He's act as a postdoctoral researcher in Department of Nanobiomaterials and Electronics, School of Material Science and Engineering, Wonku Institute of Science and Technology, Gwangju, South Korea, from August 2011 to June 2012. And from August 2010 to June 2011, I was assistant professor of physics, Bharat Niketan Engineering College. And he acted as a research fellow in Department of Physics, Alakarta University, Karaikudi, from November 2007 to July 2010. He has given many invited talks, and he has international referred publications 12, and list of papers presented in international conference is 8, and national conference is 12. Thank you, sir, for being with us today.
Thank you, madam.
Yes, sir, you can give your speak on nanomaterials, sir.
Thank you
Platform
very
is for
much.
you, sir.
Thank you for a very big introduction. And before starting, I convey my warm greetings to all the participants here. And it's my pleasant duty to thank the organizers, Rajapal and Raju's College, Department of Physics and Internal Quality Assurance Cell, and beloved friend Dr. Raja. It seems involved in taking initiatives in various areas for this program to be a success. And I welcome all the participants on behalf of this organizing committee team also, right? So myself, I'm Gopal Ram. As Madam Kalavati Raja said, I have been working in this institute for the past 5.5 years. So before that, as she said, I had completed my PhD in Nagappa University and some postdoctoral experiences in the countries South Korea and China. Right. So within a short notice, I could prepare something for this August gathering. So when I discussed with Professor Raja about having a general topic related with nanotechnology instead of just discussing research papers, so everybody is familiar with some part of research in the nanotechnology or materials in the field of chemistry, physics, or biotechnology, whatever it is. But as a humankind, these days we are using a lot of advanced technologies. So whether we are from a science background or technology background, everyone these days are having access to a lot of technological advancements, right? So I thought I would focus on that background and relate nanotechnology, how it has helped evolve those topics to today's modern era. Okay. So I hope I can start this my presentation. So if anything in between, if you want to have some intervention, you can have a hand raise or put a message, or the organizers, please, you can interrupt any time in between. No harm in that. It can be a good discussion, right? So there are a lot of people I see they want to join. Dr. Raja, should I allow them, or you will allow them, or yeah?
You can share the screen, sir. No problem, sir.
Okay. Am I full screen now?
Yes, sir. It's visible, sir.
Yes. So I with the freedom given by the organizers, I have decided chosen this topic to be flexible from the regular research papers or research discussions, right? So now here we can even it's open for even a common man or science background from a science background, or any student or any common man from any background. It will be interesting for them, I suppose. So I have tried to made my best possible. So now you can see the title. So role of nanomaterials in evolution of technologies from scrap to modern era. As you know, a lot of technologies have evolved from their basic form to the modern era. You can see one example in this slide. You can see I have mentioned communication by using just writing a letter. Then Morse code, usage of Morse code in telegraph offices. They could communicate very fast. Most of them, we can see they would have been invented for the war purpose or some emergency purposes only, right? So initially it was in wars and then in emergency purposes for telegraph offices and post offices. Again, these were also initially when they came, they were not a common man's use. They were only accessible for emergency applications, war, aircraft, air traffic, or and other post office to post office communications and so on. And after these advancement of these gadgets, these smart gadgets, multi-purpose gadgets, so we are able to now do wonders in this modern era, I can see. So there is no limit for a smartphone these days, right? So you can make your smartphone as smarter as you can. So it is continuing. So here, let me try to throw some light on which parts where we have our people, physicians, physicists, or scientists in the Department of Nanotechnology have contributed. So again, once again, this is the program schedule, right? So if there are there are students, it would have been information for them for if at all they want to visit abroad. So, but here mostly faculty members are participating. So most of you, I suppose, are knowing about these things. And I must record my sincere gratitude to my professors and fellow research scholars by then, like Professor Dr. Raja and other senior research scholars who have motivated me to participate, aspire for these kind of positions, and I could get some also, right? So now, so our background, so where we start is when we need something, some technology, some service, or some accessory. So then we start searching for that kind of right? And if it is readily available, we use that. Otherwise, we start preparing the tool which will help us avail the service, right? Then we start utilizing that. It goes on improving generation 1, 2, 3, and so on. Thereon, we do some innovations to improve that further, and finally, it would have become a totally something different from what it was at the basic stage. So in any aspect, in any department, in any department, or in any gadget, you can apply the same thought, right? First of all, we wanted some entertainment. We were playing with stones and pebbles and some balls and sticks. Then some indoor games like carom board, chess board, and later on some smaller video games, electronic machines when they emerged, the smaller video games. Now you can play far developed video games with the people at any part of the globe with the, with the advancement of science and technology and in this internet era, right? A similar strategy is applicable in every department, in every section, whether you take transport, lighting, display, communication, education, whatever medicine, whatever area you take, there is a lot of scope for these things. And why I insist these days is these days all the technological institutions are insisted to have some innovation club, right? Institute Innovation Council or club, something. And we are all advised to encourage students to take part in hackathons, and students can come forward to put forth their innovations, some models and some prototype devices and some concepts, and they can extend the same as an entrepreneur. So when they complete their course and come out, they can become as an entrepreneur. They can be the boss of their own business. So this thought has been repeatedly being insisted in our institutions, like this technical institute. So I thought these kind of discussions would be beneficial to many of the faculty members, and it is needed the most these days. So I continue in this aspect. Maybe this has been prepared only based on my own thought and interest. I would have omitted something, and I would have exaggerated somewhere where you had not expected, but something could have been missed where which you had expected. Okay, as much as possible, I have tried to relate it with this nanomaterials and the nanotechnology. So where we physicists and chemists or material scientists have contributed. So first of all, to think about a big heart, a great man, Nikola Tesla. He was a dedicated researcher for his lifetime, right? So what he says, what one man calls God, the another man calls the laws of physics. Okay, so it is that deep, right? So if you understand those laws of physics and start applying, these are those having those deep meanings. right? So when we only the small logic or concept, when it is whether it is applied for a small scale laboratory experiment or small calculation in the higher secondary school, or whether it is applied for a satellite launch vehicle, the concept is the same and it works, right? So in that aspect, these words are really important and motivating. And as you can see, whether it is tangible or not, whether it is related to our material science and nanotechnology or not, but the idea was a giant leap, I would say. Till now, it has not been realized. It has not come to the existence so far. But the glimpses of this idea in a small scale has come so far. What is the idea? Now look at these wave structures. So this was one of Nikola
Dr.
Tesla's.
Gopal Ram, sir,
Yes, yes.
slide is not movable, sir.
Is it not moving?
Yeah, yes, sir, yes, sir.
Moving?
No, sir.
Moving on. Okay, so then I will have to switch to the. Now it would
Ah, yes,
move.
sir, yes, sir, yes, sir. Yes, sir, yes, sir, yes.
Yeah, so this is the same
Yeah, yes, sir. Now it is moving, sir. Okay, sir.
moving. So can you see
Yeah, yes,
this
sir,
is
yes.
what? So I
Okay,
continue
sir,
in
okay,
this
sir.
mode. Sorry
Yes,
for
sir,
the
yes, sir,
inconvenience. Yes,
yes.
this
Okay, sir.
situation happens in many times. Right? Maybe
sir.
we don't know. Maybe our the operating system or something. Thanks for pointing out, Dr. Raja. So, I
Okay,
will
sir. Thank you,
continue.
sir.
So as I said, so what one man calls God, another person calls the laws of physics. Right. So based on that thought, so the great mind Nikola Tesla has initiated something. His idea was delivering electric power or transmitting electric power, just like the radio waves, to throughout the entire globe, right? So every common man can have access to electricity, just like whoever has a radio in hand, they can receive broadcasting from any part of the world, right? So it was his idea. So he had several such ideas. One of his greatest idea was production of alternating current from this hydroelectric plant, which was constructed at Niagara Falls in the United States, right? He was the first person to successfully demonstrate 5,000 horsepower of alternating current from the hydroelectric power plant, which he had a patent for only 1 year. Later, he failed to renew the patent, so he could not get the great, huge revenue from that, right? So before that, all electricity was direct current only, right? These days, we can connect umpteen number of devices and gadgets, so all in alternating current, right? So it has a lot of advantages when compared to the DC, right? So he was the instrumental key person in bringing this out, demonstrating the first successful production of alternating current power for 5,000 horsepower. It's immense, right? Now, so now we are entering into the department of lighting. So as we know, so these are some of the natural lights. The first one on the left top, we can see this is the light from nebulae, stars, and the astronomical heavenly bodies, right? Whether it is a nebulae or a comet or a meteor, everything would emit some light. So their principles, the emission principles may be slightly different from where they get the light, maybe some slightly different. Some may be reflecting, some may be burning, some may be producing heat and light as our sun, right? So you know these things. These are solar flares coming out of the sun's outer surface. So there, this fusion, this has anyone had a look at this lighting, this phenomenon of lighting? I hope in our region of the earth, it's not possible for us to witness this one. But this has been recorded in some other part of the globe only, right? What is this one? This is called an aurora, right? Aurora borealis, if you can extend. So you can. This name appears weird and strange, right? Recently, several times I could see these details in some television. For example, this uh, BBC television. Sometimes they used to show some small clip of these things. So these are lights appearing naturally in the atmosphere. So when this Earth's magnetosphere disturbed by the solar wind, The solar winds also have some magnetic field in that. So when they interact with this Earth's magnetosphere, there is some disturbance in the electrons and the protons present there. Some transformations takes place, which result in the formation of such a colorful displays. Okay, so whether it is possible to demonstrate here in the equatorial region of our Earth or in our region, we don't know. But similar things are possible to demonstrate, to be demonstrated with the laser hologram, right? These days you can show anything on in the air using this laser hologram to any size required. So the technology, what I mean to say, this technology has developed to that much. From where did it develop, right? So these were naturally occurring. So how the first human started getting light from? Now look at that left top image. So this is a burning torch, okay? So this is the caveman's torch. So it comes with heat and fire. It also produces light. So the light is a byproduct of this fire and heat. So whether if you want to heat, you have to burn something. If you want light, then also we have to do the same. So there we are sacrificing something, right? So if it is completely burnt out, and it has to be exercised with due care. Otherwise, it is harmful. It produces a lot of heat, or it can burn, continue burning a lot of our important things which we don't mean to burn for. Okay. Later, it has improved today's. In today's scenario, it has all improved to these kind of gas jets. So by using these, you can cook, you can cut, you can do many such wonders. So what is the difference between this color and this color? Here you can see it's burning in a blue color, right? This one is in a reddish yellow color. Sometimes you can also see some blue flame there if it burns completely. So what's the matter? If it gets more oxygen to burn, it can burn completely, then it appears blue in color. If it doesn't get sufficient oxygen to burn completely, and a lot of these carbon particles are floating there with unburnt means, then it will change the color. The presence of carbon particles change the color to yellow or red. If more unburnt particles are there, it appears red. If lesser unburnt particles are there, it appears blue. So if you look at a candle's flame, then you can see all these different regions in the same flame, right? Then with the invention of this great man, Thomas Alva Edison, we could see an electric bulb, right? So there, after the invention of electricity, and after testing several materials for being used as a filament, right? Then he came to a conclusion that he finally found that tungsten filament could be a useful one for this incandescent lamp. So as we discussed in the previous image, here also it produces a lot of heat. So initially, when the tungsten, so how does it emit light? So here also again, light is a byproduct, and it is not the first and foremost product. So when we supply electric current to this filament, because of its high resistance, it starts heating up. When it is heated to heated to the most, then it starts glowing, right? So this is how we get light from this incandescent lamp. But what was the necessity for improving this one? As I said, if we talk about we need something, we search for that and find something and start using that, then we prepare and start using that. While utilizing that, we want that to be improved. And what we do? So we make some alterations. We try to improve, innovate something, and redesign the mechanism and the design itself, right? Right. Let it be aside. So meanwhile, in the nature, apart from these astronomical bodies, we also see life from these small creatures. Not only these bees, right? Fireflies have such a lighting in their body. Some kind of algae, fungi, and also some snails, some frogs, some fishes also exhibit this kind of bioluminescence. How these fishes and fishes can exhibit bioluminescence? They are not naturally bioluminescent. When the fishes consume some luminescent organisms or fungi or algae, so they accumulate in their body, which appears like they are emitting light, right? So the light is not originally from the fish's body, but from the small organisms, algae or fungi, which were consumed by the fish. So here, in this case, this is naturally a brilliant lighting, right? So you can see a flock of birds accumulating together at one place. It appears like a beautifully lit garden. Okay, right. So what is the principle behind this? What is the mechanism behind this one? It can also be some motivation, inspiration for some kind of innovation, you can say. So these humble creatures contains this adenosine triphosphate, and they also have this luciferin, this light producing protein. With this help of this protein only, it could emit some light. And also there are certain magnesium ions present in them. It combine all these things, form a complex. When these complex mix with the molecular oxygen, then they can react, and the end of the product is a beautiful light, as we saw in the previous slide. Okay, right. So this humble creature has something awful to demonstrate to us. Right? So we have a lot of things to learn from this creature. This creature does have only two senses, right? Yeah, this could be really a good inspiration to look for something where there is no other source of light. So this is also some other source of light. If you can produce a large amount of such algae or fungi, even without any electricity or any power supply, or not without feeding anything, there is a possibility. So of course, I hear that some in some directions such kind of research are going on, but we don't know how far they are successful. Up to what scale they can scale up, also not known so far. Now we are entering into a revolutionary part of this lighting system. So now you see a name of a great person, Professor Isamu Akasaki. He's a Nobel laureate, right? Let's see what his work was. So what he says, it was proving extremely difficult to produce a high-quality gallium nitride crystal, which is necessary for controlling the material's electrical properties. So what they have done is a blue LED. For that blue LED, will you believe they have fought for a decade or more? Okay, so the people to bring this out, to make this blue LED successful, they fought for more than a decade, almost 15 years, right? What was the biggest challenge there? The biggest challenge was to produce high quality gallium nitride crystal. Oh, how you can understand our how we are all related with these kind of research works. You synthesize by any solution route or a vapor route or some electron beam route, solution process or high temperature process. We are doing something, some growth, nanocrystal level or thin film level or bulk single crystal level. But we're all preparing crystals or some layers. Okay, so we're all bothered about the quality of the layer. As much as possible, we try to improve the quality. But there, they also could do that, but the quality produced was not sufficient to prove that, right? So, but they still believed that it was possible if we improve the quality of the crystal, right? So that was the ingenious of these people, and persistently they fought for the same. So they have also thought of using zinc selenide there as an alternative for gallium nitride, but zinc selenide has many disadvantages when compared. So they could be chemically unstable, right? So in long life, their efficiency may diminish, right? So finally, he was convinced that if he could improve the quality of the crystals, the blue LED would be realized. So was that this much challenging? Was that much necessary? Why only blue LED? The red LED and green LEDs were already discovered, already in the market in 1950s and 1960s respectively. But only these blue LEDs were not available there. So if at all they have to produce things, means they have to mix other color lights and put some yellow filter to make it appear like blue or something. Okay. So the need for this blue LED was increasingly demanding. So people working in that area started realizing the importance of that. and they could foresee the big market for this blue color. We are not able to understand now, so when we go to the forthcoming slides, we will be able to understand. Now we are looking at these great people. So Isamu Akasaki and Professor Hiroshi Amano. So these two people are from this Nagoya University in Japan. And, another Japanese person, Japanese American, you can say, Professor Shuji Nakamura. He moved to USA by the same time when they were trying there in Japan. He also started trying his own effort to prepare this blue LED. What is the route? The only route is just preparing gallium nitride nanorods, high quality gallium nitride nanorods or nano layer. So now here also I'm sharing our own experience with the preparation of gallium nitride nanorods. Because you can see we have tried our own gallium nitride nanorod, single nanorod diode PN junction. Okay, you can see we have prepared single nanorod PN junction. So how was it prepared? So we used the method of hydride vapor phase epitaxy method. But whereas these veteran people have utilized this metal organic chemical vapor deposition, right? What does the name convey? Metallo organic chemical vapor deposition. So deposition is able to we are able to understand vapor deposition. That vapor is produced from a chemical reaction. And what is the metal organic, right? So these days you can see CVD many places, chemical vapor deposition. So if you supply the metal in the form of metal organic vapor, for example, ethyl gallium or methyl gallium, something like that. So if you want to mix the dopant with the gallium nitride, their magnesium will be mixed in the form of metal organic vapors, right? So that much high quality controlled flow of vapors were required for the preparation of these P-type gallium nitride. As you can see in our work, what we have done is we have used this graphene layer. This graphene layer is produced by this regular chemical vapor deposition method. So you can see we introduce a copper plate into a CVD.
Dr. Gopal Ram, sir.
Yes.
Sir,
Yes.
voice is low quality, sir. Please, mic is nearby, sir. Please.
Yes. So when we use this chemical vapor deposition, we introduce this copper sheet there inside this CVD chamber, right? So when we pass methane gas at 1000 degrees Celsius, then you can get this graphene layer there, right? So how to transfer this graphene? So you can understand this is a one monolayer, one atomic layer thick material. So now you can understand how thin it is, right? And it has to be transferred, but it because of its natural quality, it is very robust, it is very strong. Even being at that thin level also, it exhibits good strength. So it can be floated to some copper etchants. Then this copper will be etched out. Now this graphene alone will be floating like a net. Then it will be fished out on the silicon dioxide substrates. Now we have a conducting layer on this silicon dioxide substrate. Usually to grow these gallium nitride materials as a single crystal, we need another hexagonal buffer layer. Fortunately, this graphene also is a hexagonal material. You can see these hexagonal patterns there. Otherwise, usually sapphire would be used there, or some aluminum nitride layers would be required there to initiate the nucleation of this gallium nitride. So the compound gallium nitride cannot be just formed by a chemical reaction very easily. You cannot directly supply. For the case of, for example, if you want zinc oxide, we need just oxygen and zinc metal. They would react and form zinc oxide. But in this case, this nitrogen is an inert gas. It directly cannot react with anything, and this compound cannot be directly formed. So in our hydride vapor phase epitaxy method, we used HCl and nitric acid, HNO3 gases, and also this gallium metal to produce this gallium nitride. Naturally, it will be grown in this N-type material by its nature. And if you want another P-type, then we have to introduce this magnesium doping. Can you see this one? I'm coming to the point. Why magnesium is so important? What was the challenge for those veteran people to prepare this blue LED? Even though you dope magnesium, magnesium is present there in the nanomaterial, in the nanorod itself, and you can exhibit some p-type property. If you check whether the magnesium is there, yes, it is there. But if you expect the p-type performance there, it does not do the job. So how to do that? How to make this? It's just sleeping there. It is there. It is hiding there, but it is not working. So we have to activate that. Okay. So in our case, we just increased the concentration of magnesium so that we could get this sufficient activation of magnesium and this P and N performance from the same single rod, right? But for those people, they came forward with their own intellectual ideas. So these two people working in different places at the same time. Initially, these people just heated this N-type, P-type material to activate those magnesium traps, whereas this gentleman made an UV radiation there to activate those magnesium atoms present in this P-type gallium nitride, right? So here is the here is the model which was proposed by them, which was actually demonstrated by them. So the first one was demonstrated by the team working in Japan, Hiroshi Amano and his professor Isamu Akasaki, right? So they fought with the government to get huge funding for the purchase of a MOCVD growth setup, right? And this gentleman, with the support of some industry, Shuji Nakamura, he could also start doing his MOCVD. Right. As you can see here, what they do, this is the setup of an LED, and what is there inside this small place. You can see there is a sapphire substrate. Above that substrate, you have a gallium nitride buffer layer. Then the N-type material is prepared. Above that, and again another N-type aluminum gallium nitride is introduced. Then zinc doped indium gallium nitride and p doped aluminum gallium nitride. Finally, p doped gallium nitride. So we need only gallium nitride, right? So what is the job of these guys? Indium gallium nitride, aluminum gallium nitride. So these are very thin layers, as thin as 10 nanometer or smaller. So these are called multiple quantum wells, so that they can improve the efficiency of lighting there, right? So even though these just a mere p-n junction, as we have demonstrated here, even though it works, so with this one, did we get light emission? No, it was not possible, because it will require we need to increase the quantum efficiency, right? So to make that possible, the introduction of such multiple layers called the multi-quantum wells were necessary. So with the introduction of those multi-quantum wells, so blue emission was possible. As you can see, later it was improved to blue laser also. And based on gallium nitride, they have developed a lot of such high electron mobility devices, HEMT transistors, you can say. A lot of work have been done by this team. And you can see now, you can understand what a big giant leap has been made to come to this level. So we started from burning lamps from oil, then this incandescent lamp, from that discharge tube. If you fill different colors, different gases inside this discharge tube, then it can produce different color lights. Later then this intermediate, we also saw these compact fluorescent lamps, which were even more energy efficient. And finally, now we are with these glorious, colorful LED strips. You can decorate any these LED strips, and any intensity is possible with these lights these days. You can just go on increasing the wattage. What's the advantage here? So these LED lamps help us preserve 40% of power consumed for lighting itself around the globe. So it is measured in the United States itself. It has reduced 40% of power consumption, which was previously used for lighting alone. So in the long run, it can reduce a lot of power consumption for lighting purpose, right? Now with the advancement of this, you can see we could achieve such glorious indoor lighting with our homes, which are tuning to our mood, right? So these days, mood lighting you can hear about, you can see in many places inside the car or inside your hall or a bedroom or dining space. A lot of colorful combinations are available. You might have seen in advertisements in Philips lighting. So if you choose the light in your mobile phone, app-based control are possible for this lighting. Where's the light here? So you can look at the black rod, right? So this rod is consisting of this light. Whichever color you want to shine, it will change, right? Based on the application, you can change. Why we want to change the color? So it is related with our humans mindset, right? It bothers their mood. You can understand these days the blue light coming out of our handheld devices, laptop screens or mobile phone screens, they postpone our sleep. Mm. They prevent secretion of melatonin in human body or brain, so they postpone the sleep. So if you were looking at these gadgets late in the night, this blue color, without knowingly we get disturbed by this blue color. Then how to get rid of that? That's why these days we have in a mobile phone night mode. So there it reduces the blue color as much as possible. Then it changes the shade from blue to an yellowish shade, right? You can see now you're looking at the sunset inside the home. Is it possible? Can you see the reflection of a setting sun inside your home? This is awful, right? This is very glorious, but everybody would be delighted if they can see this in their home every day, every time, whenever they want, right? Even if you locate your house in these places where you can see sunset every day, uh, throughout the year it may not be possible around the globe. So from place to place the location would vary. Someday you get in your home, someday you may not get at that time in your home. Some object will be obstructing that from appearing in your home. But this is not the natural sunset. So this is an artificial sunset which was prepared, which is available in market these days. You can see with the invention of this kind of lightings, we can make wonders by using these different lighting setups. If you want a natural sunlight, yes, it is. It appears if it mimics the natural sunlight. If you want a rainbow, yes, you have. And sunset color, yes, even the sunset red is also available. So occasionally you can have this to have the evening kind of mode, right? So we don't understand the importance of these different color lights. We just pass through this because we are in the equatorial region of our year, where we have enough sunshine throughout the year. We see the sun every day, almost. If not, it is cloudy or in this uh, densely clouded rainy season. So it's not a big issue for us. We are not much affected by this not seeing the sunlight or not having sunshine on our body. But you can see in places, cold countries, people used to sit in the beaches to have sunbath, right? So they need more vitamin D from direct sunlight because they don't get enough sunlight throughout the year. But here we are bestowed with the sunlight for the year. There, this lack of vitamin D not only disturbs their well-behaving, their sleep cycle, their mood also. If you cannot see sun for 2 or 3 days, how will you feel? All the time, if it is night, how it will feel like? But there are places on the earth where you cannot see sun for at least 20 days, 40 days, or 2 months, or there will be sunshine for 20 hours of a day throughout. Even if you travel to northern or northeastern parts of India, in Calcutta, you can see a very bright sun early in the morning by 4:30 or 5. You can read newspaper in that bright light. This will persist until 7 p.m. in the evening. So in the summer months, you can have the sunshine up to 7 p.m. in the evening. But which is not the case in our place, right? From geographical location, these varies. Now, if we move towards this polar region, it is understandable that they may have sunlight for longer durations, and some other duration of the year, they will never see the sun at all. Or if at all they can see the sun, it appears, it rises at a time within 3 to 5 hours, it sets again. Again, the night comes, right? There, people need this kind of mood lighting. With the help of this kind of mood lighting, with the several setups, you can feel like it can move with your circadian rhythm. What is circadian rhythm? So this is the rhythm which is governing our sleeping cycle of human body, right? So one small improvement, how much it is uh, influencing the human life, you can see. So with this help of this is the same light. We have not changed anything, just with the different additional filters. We are able to change different lighting and make it feel like we are on at particular part of the day, right? When you are at the lunchtime, if you see like this, then you really feel that you are at lunchtime. If you see this one and you are experiencing your lunch, means we may not enjoy the ambience. One or two times it doesn't matter, but throughout the year means, or long duration means, it's really very difficult. It affects the mood of the human being there, so it affects the circadian rhythm there. So this is the it is psychological lighting, psychology of lighting, so that it can make people feel like they are in their natural sleeping rhythm or sleeping cycle or their circadian rhythm. So it varies from person to person on the different parts of the globe, right? With all these technical advancements, what is the future of lighting? Can anyone? I expect some answers. What is there any additional step for lighting? Is there some additional necessity for lighting? What is the future of lighting? What is the next step in this one? So I started from the basic one and I started extrapolating, right? As you can see, I started extrapolating so that you can understand what is the need, what is the next one, which one we may need. So the answer is lying there. It is the natural sunlight. Now you're looking at pictures which are not glass windows. These are lamps. Can you imagine? Can you believe me? These are lamps which portray the natural sunlight. Suppose you are living in an underground apartment. Why would we live in an underground apartment? Here we have a lot of space. Think some countries, some regions where there is a huge apartments, 25-story building. There will be some 8 to 10 floors below the ground. Those are all basement apartments or underground apartments. There, they will all the time throughout the year, they will have only these electric lamps, right? There, these kind of mood lightings are needed. So this one will make them feel like really they are experiencing a daylight, sun's daylight, right? So this will really can have a effect on their psychological behavior. Okay, so this will improve their feel of the day. So we can see if we shine blue color, so less melatonin secretion in our body, and then we feel really very active. And if we continuously look at red color, more melatonin can secrete, and this can allow us to sleep, allow us to rest, and can induce sleep. Right. So these are two extremes. So at night we don't want this blue color to be seen. So we have to control our devices also to the night mode or change the background so that it appears less blue. Right. So this is the future of lighting. So even the underground buildings where they cannot see sun anytime, or if you are inside a gymnasium or inside a restaurant which is underground, if you want to have a natural daylight, so the entire wall can be made a big lamp. A lamp can be made of the wall size, and it can feel like you are inside a glass wall, right? So this would be soon possible. These days, these are expensive, but uh, companies are striving hard. But in future, definitely, our home also will be decorated with these kind of lightings, if at all there is a necessity for a natural daylight, right? So these days we do not use so much uh, glass materials in the construction. So these glass materials helps reduce power consumption for lighting. If we have enough natural daylight, then we don't use electric lamps. We don't spend power for lighting purposes. Where we cannot have direct sunlight, daylight, then these lamps comes to our help. Now, looking at this image, you can see. So how many kind of small steps of improvement have been made to move from this letter, telegram, telephone, email, and to the today's Twitter or this WhatsApp, Telegram, and the video calling facilities, right? In real time, you and I are connected from different places, right? So there comes the wonder of this technology. So we are all connected with the optical fiber cables, right? Or satellites. So the small principle of total internal reflection there in optical fiber cables help us communicate with the speed of light, right? You know. So how could we reduce these devices to small pocket or handheld device? So there comes the revolution of nanoscience there, nanotechnology there. So here now we are looking at some technology which helped us to reduce the memory size. That is called magnetoresistance. So what is that? It is the change of resistance of the conductor when it is placed in an external magnetic field. For example, ferromagnetic metals like iron, cobalt, and nickel exhibit this property. They have a natural resistance, right? So these are good conducting metals. They have some minimum amount of resistance there. When these resistance measured in different magnetic fields, they are different, right? So it was an accidental discovery so early, 150 years ago, right? What was recorded? I found that iron, when subjected to a magnetic force, acquires an increase of resistance to the conduction of electricity along and a diminution of resistance to the conduction of electricity across the lines of magnetization. So this is called anisotropic magnetoresistance. The same material behaves in two different ways when the direction of magnetic field is changed, right? How did it help? A small spark that helped these giant, great scientists, Peter Greenberg and Albert Fert. They got the Nobel Prize for invention of this giant magnetoresistance. What did they discover? For the discovery of giant magnetoresistance. They shared Nobel Prize in the year 1939 for this discovery. What was the discovery? When materials are reduced to just a few atomic layers, a few nanometers in thickness, their properties change. What did they do? They used the same iron, cobalt, or nickel. They both were trying these things at different places at the same time. He's a German professor, and the other one is a French professor, French scientist, right? They have found the same thing at the same time by using similar strategy with the same materials in slightly different styles. German professor Peter Greenberg used thin layers of iron and two iron layers separated by a chromium layer. Ferrous iron is a ferromagnetic, whereas chromium is not. That's a non-conducting metal, and iron is a magnetic conducting conductor. Okay. But the strategy, the key idea there is we have to prepare them in few nanometer thickness. 50 or 60 nanometer thickness was utilized. With that, they could see that there is something changing, and current is passed through one direction because of the spin direction of the electrons present there in the surface. They are spinning up in one direction. Now their resistance is changed one way. When the current is flowing in the opposite directions, those electrons turn in the opposite direction. They exhibited their spin down. Now their conductivity has slightly differed. So whether you want to fix it in the upward spin or downward spin, you flow the current in one direction to make it upward spin, or you change the direction of flow of current in the other direction to make it downward spin. So when you leave it as it is with the upward spin, that means it is 1. When you leave that cell with the downward spin, that means it records the data 0. So this way, these days you understand, you know that all the data is recorded in the binary format 1 and 0, right? So this is how the 1 and 0 are recorded in small regions in nanometer level at these recording disks, right? So with the help of these things, they could reduce the size. You can see. So this is you are looking at the first computer which Charles Babbage had invented, right? Several hundreds of years ago. Look at this. This device has to work for a long time to do some basic arithmetic calculation. To record the data, we need such punched cards. To retrieve that, we need to have reels of such punched cards, which are really very, very heavy, and they also occupy huge amount of space to save. From this level to this level, we have slowly improved, and finally, it was a giant leap with the help of this nanotechnology, right? When iron and chromium were prepared consecutively with nanometer thickness, and when current flows through that, we can change the spin of the electrons there. And by this, we are able to record the data, whether 1 or 0. So when you retry that again, there is another reading arm which will retrieve the data. If it was upward spin, then it will record 1. If downward spin, it will record 0. When the reading arm grazes through many such cells, it will get a train of a binary digit number, which will then retrieve your detail, whether it is an audio signal or a small color pixel. All several such data will be integrated to give you the output, right? So now we can really feel proud that Sanana technology has helped us make a giant leap from the previous era to this modern era. There is also another team which has contributed tremendously. They have just contributed only one thing, but they have really, really revolutionized the world. Who are they? They are William Shockley, Walter Brattain, and John Barin from United States of America. They were awarded this Nobel Prize for what? Could someone guess? I expect somebody guess.
Superconductors, sir.
Now,
The transistor, sir.
transistor, very good. Thank you. Thank you. For the invention of transistors, they were awarded Nobel Prize. Right? Why transistors is that important material, important device? And now we don't know. See, this was you're looking at the first transistor developed by these scientists at the Bell Laboratories in the United States, right? So this is the bottom one is the image of the transistor. The top one is the scheme, how it was prepared. So there is a plastic frame, and then there are two gold foils wedged to the P and N type germanium. Okay. So in addition to the diode, it has one more P or N region. So there we have two p-n junctions. With the help of this one, we can make several number of switchings in fraction of seconds, right? Millions of operations, millions of time we can do the same, right? But initially it was device like that. It was so big, it was a hand size, right? You can carry it in our hand. So this was that size. But these days you can see with the help of nanotechnology, these have come down to atomic layer thick. So now we can see several papers coming out with the monolayer transistors, thin film transistors, right? What our monitors are called. We are emerged from CRT monitor to TFT monitors, right? Thin film transistor monitors. So, and also we have a lot of circuitry you can see. So with the invention of these devices, we could move from vacuum tubes to modern integrated circuits. So those days ancient, before the transistor, we were using these vacuum tubes. So audio will be there. If you want to listen to this radio means uh, you have to turn this radio on. It consumes a lot of power heating those vacuum tubes. Then only start working, and it will produce a lot of heat and go off. Right, huge amount of power would be wasted there. And it was really very heavy. Then it produces some noise from these heat, right? So it was really uncomfortable to use those devices. But later on, with the invention of these transistors, it was revolutionized, right? Now, this only helped to prepare pocket transistors. So now you understand how we have emerged from this size. So these kind of communication devices were in use in warfare. You can see the people wearing the uh, dresses. You can find that they're all soldiers on the warfield. So these were the devices which were used. If you look at this, some videos in World War, you can see World War I. You can see some devices being used like this, right, for communication, for receiving information and communicating. You can look at this one, how hard it would have been. Now you can see evolution to small, pocket-friendly, handheld device, which can do wonders. Right? It all was possible because of the nanotechnology. Not only with this device. Now this device is prepared at the nanoscale. As I told you, I showed you in our laboratory we did this single nanorod PN junction, right? So one nanorod can behave as a diode. So we have tested this one with, but still one single nanorod also would behave as a diode. Now these days they have gone even further to make these kind of thin layers. Now you can see this one graphene layer. These are latest advanced 2D materials, transition metal dichalcogenides like molybdenum disulfide, tungsten disulfide, tungsten diselenide, and so on. There is a huge family of such materials. These materials, when peeled off, they would perform this operation of a transistor, operation of a thin film transistor. And in modern days, these ceramic oxide layers are also being used as transistors. Amorphous oxide semiconductors, indium gallium oxide, mm, indium gallium zinc oxide, indium magnesium zinc oxide, indium magnesium iron oxide. There's so many ceramic oxides are being studied these days. They also perform these transistor performance when they are prepared in the nanometer scale, right? And apart from above that, thin film or monolayer transistors are also being reported these days. Soon, our devices will be even more simplified. Their size will be reduced down further, and they will become even more smarter. Why we praise these integrated circuits? So there is one law called Moore's law. Have you heard about that? So every year, you can see computers are becoming uh, smarter and smarter. You can do millions of operations. When you compare the computer with the previous one, 5-year or 10-year-old computer, now you can see a lot of processors improved a lot. Pentium 3, Pentium 3, and now today we have a i5 and i7 processors, which can turn on quickly and turn off quickly. So even to turn on and turn off the computers also, it takes some time, right? So if you get a chance to look at the old computer, maybe uh, our faculty members of these days, they will be knowing, but these days students do not know the difference between the Pentium 3 computer and these days i7 computer. So I feel I found it was necessary, and it's our responsibility to inform the students how much we have improved, right? So I used to discuss this kind of history and present days improvement and what will be the future like this, in such a way to extrapolate the thought process, so that there can be some steps, some initiations for innovations possible, right? So I thought this would be appropriate to share with our uh, fellow faculty fraternity, so that they can also share this kind of information, disseminate this information to their own students, and encourage them to participate further enthusiastically researches which can improve one step further. Even if we make one small step further, and so on, in years, it will make a giant leap, we can say, right? Now we can see from this level to a smart, simple, pocket-friendly, on-the-go pen drive. Okay, how much we have transformed. You can see there was an era of utilization of a floppy disk. You can record on, you can save only 1.44 MB. Now, if you tell these details to the students, they will laugh at. Now you can see 2 terabyte pen drive has arrived, right? So all with the help of these these discoveries with the utilization of nanomaterials and technology. Now these days you can see these are we can in fact draw transistors. Okay, sub micrometer sized MOS to thin flame transistors by phase mode A from lithography. You can write. So if you want a transistor in these in a particular pattern or fashion, you can straight away write using this A from tip to prepare transistors on these 2D materials like MOS2, and many such many such work are being published these days, right? And you can see a real demonstration of a monolayer transistor. So here, this one is not a bipolar transistor, but field effect transistor. They construct a source and drain there when we have a back gate. When we deposit metal on this monolayer, and then we can study their performance. They perform. They perform. So this is the glory. This is the magic of these nanomaterials to help us further and improve and reduce the sizes of the gadgets and improve their smartness, improve their capacity, make them more efficient. Here is another one more small invention to help this kind of research feasible. If you want to really perform this one, if you want to really perform this measurement of a transistor for a monolayer material, we need to prepare this gold contact. So gold evaporation may be available in many places, but to make a mask of this size, so this flake also itself would be less in micrometers. So we cannot precisely place our mask there in micrometer to coat gold on this monolayer or multilayer, right? So here, but if we have those flakes in the liquid media, then we can spill our flakes on these what? So these are all silver electrodes. At any point, if you get a flake floating on there, if it is attached to that, then you can start making measurements. There you have this 4 probe available. If you got a flake at this point, then these 4 probes are available for you to do measurements. And here also, if you had a bigger flake or if you had some smaller flake in different spots, there are many such 4 probes available. It's a small device I saw in the market online, right? Really a good invention. This can help you make this research in a pocket-friendly manner with a low budget available, right? So it is our responsibility to look for such small innovations in every arena of our every area or every place in every department, wherever we come across, as a teacher, as a researcher, and as a scientist, as a physicist. We have to observe it and reflect the detail to the forthcoming student community, and we can ourselves utilize the same to improve it further, to make some small step or small improvement or innovation in any of the fields, right? Here you can see, now again, I insist the same statement: need for something and searching and finding the same, preparing or finding the ingredients and preparing the tool for us, and utilizing and improving, innovating and reinventing the same for the future's miraculous devices. As you know, this was once discussed. It was not possible. First of all, the touch screen was not possible long days back. As you can see, this is a pager device which was initially came into existence before this mobile phone. Many of us may be knowing these pagers, but it was the service was provided for only some shorter regions, mostly in some major cities. Before this before this come into all the cities, then the other technology has taken over, the technology of mobile phone. That was even more profitable, so companies immediately jumped to that technology. Right? Later on, the touch screen came, and now these foldable screens. In future, there is a rollable screens are also being proposed. Some companies have already developed televisions, rollable televisions of a meter size, 1 meter size, 1 meter diagonal or half-meter diagonal. The TV does not obstruct when you are not watching. When you are not watching the TV, you can roll it up and place it like a small bar. Only when you want to watch the TV, you can unwind it and start watching it. And this is a modern, sophisticated, advanced, smart computer proposed, right? So the computer itself would be a small device. So it will project a keyboard for you. Whatever you type there, it will be recorded by the sensor there. And then the data and the storage also, as you can see, has been reduced to a very small size. Enormous amount of data can be stored in a very small size, or now with the help of the internet, you can store the data in a cloud. The connection is possible throughout 24/7 everywhere in the globe these days. So there is a feasibility for expecting small computers, smart computers like this in future. This was also a proposal. Several proposals, when they were initially proposed, they were thought of idiotic, impossible, and they won't work. But later on, slowly, the human kind have come to see the successful existence of that device in the regular life and reality, right? So many times we see this one, this right-hand side picture, as if something is displayed. You don't have to carry your mobile phone. This band will behave like your mobile phone, and it will project the details onto your hand. Still now, I don't know whether it is true or not. It is really a device or not. It is a real one or just a cooked up image. But still, this idea, this stupid idea, can become a possible one day, right? Can become a reality one day. So the humankind really has a more sweeter days coming in future with the support of nanotechnology and engineering, with other all advanced materials and science. So with this, I come to a conclusion. Hope I have communicated some of the details which I wanted to, right? So now you can understand the pathway, right? So the ancient method, then the medieval technology, evolution of some other technologies, and the improvement of those technologies to the present modern era. So this was the concept which I wanted to share with you, faculty fraternity. Thank you. I am happy to receive your comments, questions, or discussions, if any. Now over to Dr. Raja or Madam.
Dr. Klavadi ma'am,
Okay, dear participants, do you have any question, please?
Dr. Gopal sir, Gopal Ram sir, excellent presentation, sir.
Thank you. Thank you very much. So you can put your comment. The participants can give your comment in the form of a text message also, or if you have some interaction, you can raise your hand. You can please unmute yourself and please feel free to talk.
Sir,
Yes,
good evening, sir.
good
I'm
evening.
Dr. Pandishwari from Sri Ramakrishna Engineering College, Coimbatore, sir. So it's a very wonderful presentation. A lot of
Thank you, madam.
information, new information, especially for the young researchers like me, sir. It's a
Yes,
very interesting presentation, sir.
yes,
Sir,
madam.
I have one question, sir. You're mentioning about the transistor and all. So,
Yes, madam.
what are the testing area for this particular field, sir? Because we are a young researcher, we are propose something uh,
Yes.
in the form of
So,
proposal. So, what are the testing area for this particular kind of transistor and all, sir?
so when it comes to material science for devices or semiconductor devices, the eternal one will be right, transparent, flexible, biodegradable, wearable, cheap. If your out end product, your resultant product has having many of these properties, then it is a better one than the one available in the market. That's a strategy, madam. And now in the case of uh, electricity or electronics, we are going wireless, right? You can see we were using phones with wires, then mobile phones. Once it was thought, phones without wires were not possible. If it had been there, then it would have been convenient. Then the walkie-talkies came, the handheld devices inside the homes were started coming. After that, the real mobile phone also came. And then now with the help of these mobile phones, we listen to music when we are talking or listening, we use the headphones. Now we can see within a past 5 years or 10 years, how much it has improved. The headphones were there right since the walkie-talkie time or this Walkman time or transistor time. Now Bluetooth audio headphones, right? So you don't have to connect it with a wire. So it is straight away connected with the Bluetooth. Again, small and small improvements. Now the forthcoming technology is to charge electric vehicles. Now you can see you can pay your toll at the toll gate in electronic mode without any contact, right? So when the COVID-19 was striking all around the world, these UPI payments helped us a lot. You know that. So without touching other persons, without touching the cash itself, we can pay money. So we don't have to even touch the card. Right? We don't have to swipe our card to the swiping machine. By UPI technology, we can straight away pay our toll. But without even touching our mobile phones, these NETC machines, that is the National Electronic Toll Collection Department, has these toll collecting machines at their toll collection booths, right? So just when our vehicle passes, from this tag, RFID tag available there, it can take money, take the toll from the vehicle, right? So these days, this is the future. So if you look at this Internet of Things, there is more such a need for this kind of RFID tags and wireless communication devices. The moment you enter, whatever you think, if you say something, you wear a spectacle, you have a mic there, if you give some information to your robot in your home or the devices in your home, everything should be on. When you enter, the light should be on, the fan should be running, or the air conditions should be ready, or the room should be kept clean. There are bots available. Soon they are about to come, right? If our research can contribute towards the future, the Internet of Things, right? So everything would be connected to the internet. So one small example would be a person going to the market. Suppose she looks at the butter, or he or she looks at the butter or some cheese, whether they have to buy it or not. Immediately they have to refer to the refrigerator in their home. These days, refrigerators are coming with cameras inbuilt, and they are connected to the internet. Straight away, they can make like it's like a video call, like meeting someone in the refrigerator, whether we want it or not. So this is the era. So in future, everything is going to be made like this. Now, what we see in space science, right? We send some vessel vehicle there in space research. We control from the ground, or we have the program. We have programmed it already so that it will work. You will do the job whatever we have instructed. Take some samples of sand, take some photographs, break the sand, break the stone, and check inside. What is the content there? What is the composition? Check it and transmit the information to us. Keep on sending photographs and keep on updating. These informations that have been already stored there. It works there. It does the same, right? So sooner the human intervention will be very much lesser. So you don't have to wash your clothes. Today nobody washes their clothes by their hand. Machines are doing that. So there are a lot of such funny or interesting proposals which may appear impossible these days or idiotic these days. Sooner or later they will appear real in our own lifetime. We will see them. So if our idea is contributing to that, then it will be really appreciable one. Tomorrow, by this Friday, in our college campus, we have a invited lecture. The topic is artificially made bio tissues. You can make tissues. Suppose some person gets injured, right? Suppose we lose some part of the bone. If we collect all the bones, then we can keep them in place and tighten that. If we lose some part of our own bone, what we do? There are bone replacement materials, hydroxyapatite. So they can be made into the size and shape. They can be machined and placed there. And teeth replacement material are already been designed. Zirconium teeth, zirconium caps, gold caps for teeth are already available. But how to compensate for the tissue loss? Okay, for example, some person has lost his muscle, a calf muscle or biceps is lost. So now the remedy has come. So that with the help of these kind of tissues, the sufficient necessary amount of muscle can be prepared and it can be placed there. If they become compatible to that body, then it starts attached to that muscle present in the human body. Then it works, right? It recovers maximum to the maximum. So a recovery from any injury and accident is partially only possible in spite of all these technologies available these days. But with the help of these kind of things, suppose such thing happened in the eye, such a sensible organ, then we understand the importance of that material in the invention, right? This way. But any small step, any small improvement is really a contribution to this field. So we can feel proud of that. At least, if not, it has improved. It gives us an experience, right? So this way also we can feel happy about that. The only thing is we must be connected to the research and the advancement in any manner. Either you guide a student or do it yourself or learn about the history and extrapolate, write something to the public, or teach school children something, right? They would really think in a different way than what we have taught, right? So definitely all these things would be a service. Just if we start speaking like this through the school children or college students or any common man, even common man, those who have not studied science or technology have their own ideas, their own thoughts, right? So if it is supported with sufficient necessary scientific background, then that can also become a fruitful idea, device to borrow. We don't know. So these you can look at these dabbawalas. Have you heard about these dabbawalas? They have a system. They bring your meal from your home to your office table without fail throughout the year. They deliver thousands of such parcels throughout in and around Mumbai, right? They are recognized by National Geographic Channel also. They are an international. They have an international reputation for their accuracy and their consistency. Even if we have some food remaining in our box, means if you return that, share my box means it would be shared to the needy person. Really beautiful, right? It's a one single idea, one small idea, but a team works to execute that idea. Not only devices and materials, the idea also, the Uber, Ola, autos, these are all small, one idea, but they connect millions of people together and provide necessary service, right? So there is a ample amount of possibilities for innovations and improvement in every arena, everywhere, wherever we see. So this is the, in my humble opinion, this is the information we need to persistently disseminate to the student fraternity of present era, right? The remaining, they will come forward with the fulfilling ideas. If you have any comment or question, please. Really, I didn't expect this much of a response for this meet. Really, thank you very much, Raja, for giving me the freedom to present this topic. When I discussed this topic with hesitation, I thought maybe it would be rejected. No, these are not possible. Our college won't accept that. But he readily came forward. He encouraged me as we were in our university days. Thank you, Raja.
Thank you, sir. Thank you, Dr. Gopal Ram, sir. Dear participants, if you have any query, please ask. Sir is waiting.
Sir, thank you, sir. Thank you for answer my question, sir. Sir, one more question, sir.
Please.
What are the futuristic view of sensor technology, sir? Because I'm working in the field of sensors. So,
Definitely, lots of sensors are needed, madam. The
yes, sir.
improved sensors are definitely needed in large numbers. As you can see these days, when we start speaking, our screen only starts blinking, right? So a lot of such sensors and actuators are needed in the future. So there is always ample space for improvement. Even the same material, same procedure, same size, everything, but the sensitivity, right? The responsibility have been improved means that is good. And if the same persists for a long time, 5 years or 10 years, then it is far better. So these are the ways, madam. So we don't have to go on looking for materials and newer materials. So the mantra for material science, I would say, is what I have learned from my colleagues. I have worked with colleagues, even though when I was working in Korea, some of my colleagues were Russians. So those Russian people, they also had a very good thoughts, right? So they propose, they extend the futuristic devices, right? Even though we are doing some working with small materials, what we have to look for is transparent, flexible, conducting, biodegradable, and cheap material for fulfilling any need for any device in any area. So this is the expectation, madam. And moreover, in addition, if you consider sensors, not only the visible region sensors, IR sensors, infrared, ultraviolet sensors, or gamma ray sensors, or some radiation sensors. So they will be useful in dosimetry. So these are dosimetries. Even though the same work is done in that area, then that receives very much appreciation because it is useful in medical field, right? So we have to channelize our interest and efforts into to the necessary place. Then our work will be rewarded or much more appreciated than usual. In my humble opinion,
Thank you. Thank you so much, sir. Professor Dhananjayan, we can wind up this session, sir.
Thank you, sir.
Thank you.
Professor Dhananjayan,
Sir, very good evening to all.
we can wind up this.
Okay, sir. Okay, sir. Very good evening to one and all. It gives me an immense pleasure to deliver the vote of thanks on behalf of our department. I would like to thank our Chief Guest, Dr.S.D.Gopal Ram. We are really enlightened with your knowledge and presence, and your session is a very helpful one for the young researchers. Thank you, sir. Thank you. Next, I would like to thank our management, principal, and the head of the department for their support and make this event a great success. Then I like to thank all the participants from various colleges and the universities. Finally, I thank all the staff members for your cooperation to make this occasion a successful one. Thank you, sir.
Thank you so much, participants. Thank you so much, Dr. Gopal Ram, sir.
Thank you, one and all. Thank you. A big
Thank you.
thanks to
Thank
everyone.
you. Thank you, sir. Thank you, sir. Thank you, sir.